Yeah. Okay, let me start. Thanks for coming, everyone. So actually, a couple of things before I start. You can all hear me at the back, right? Okay, fine. That's good. In my mind, I had something like 40 minutes for like the first half, a break, and then 40 minutes for the next half. But we'll see how it goes. It's possible it might also get over before that. And also, I think I want to keep it quite interactive, so you can stop me anytime and ask questions when you want. The second thing is that I initially thought of making it a more hands-on session where I wrote a bunch of Jupyter notebooks where you can actually code things and like you can see how certain machine learning models run, for example. I have created those notebooks, but I thought in the end that it would be better to just explain things using slides. So if anybody wants, you can ask me and I can send you those notebooks. A lot of the figures that I use in the talk will be, like I did generate them from those notebooks. So if you want to actually run them, please ask me and I can send them to you. So this is actually a talk about my master's thesis project, and it's at the intersection of deep learning and like astronomy, specifically like a component of it involved modeling a component of the interstellar medium. So I will start by talking a lot about machine learning actually. I don't know what kind of machine learning background all of you have, but I thought it might be good to start from the basics and then proceed to the more complicated stuff. So the first half will be more machine learning. At any point of time, yeah, if you feel like it, you can ask questions, stop me and ask questions. The next part will be more about something called photodissociation regions, which is a component of the interstellar medium. Then I'll talk about something called emulators, which are like a statistical model that's used to like speed up the performance of like your modeling software. And then I'll briefly touch upon like some applications of emulators and the field of scientific machine learning. So I'll start by talking a bit about machine learning. It might be very useful for you if you've not had a background, but even if you do, I think it's nice to talk a bit about it. So machine learning, the basic idea is you think of it as a way to approximate and fit functions to a data set. Your data set could be anything, by the way. This is just a random set of points that I've displayed here. And you want to say they have coordinates y and x, and you want to fit a function y equals f of x to the data. The problem is you don't know what the function is. So you need to come up with a sort of statistical way to fit this. And in that sense, machine learning is essentially trying to find statistical patterns in your data and trying to come up with a function that can fit this data. But yes, imagine you can sort of describe this function using just some parameters. Like these parameters fully describe the function, and so you want to find the parameters that describe this function. But yeah, it can be any kind of mapping essentially. It can be like points like that, like numerical points where you fit a line or whatever curve you want. It can also be text, for example, like large language models, for example. They take text as an input, and based on all of the processing that they do, they output probabilities of what the next word could be. And so they take like sentences or words as inputs and then output probabilities based on which if there is large probability for a certain word, they output that word. So yeah, with machine learning there's some terminology. Model is whatever we want to fit. The f of x, the f is the model. Weight refers to those phi, the parameters phi that you see there. And ideally we want these parameters phi to fully represent the function. And when we say we are learning a model, we want to find those parameters phi that give you a function f which can best represent the data set. Then you have this data set which is like, here it's n pairs of input and output examples, but it could be very high dimensional. It could be, as I said, it could be text, it could be images, it could be videos, whatever. And then you create this function and then you apply it on the data set and you get a sort of prediction. You want to know how close that prediction is to the true values, and you quantify that using something called a loss. It's like the degree of mismatch. And the goal is to find the parameters that best fit the data, basically. Oh yeah, okay. So So a simple example of machine learning is linear regression. How many of you have done linear? Yes, go ahead.
In this slide, how many parameters do you need? How can you know how many parameters?
It really depends. For this one, for example, it's mostly just a straight line, so you need 2 parameters. If you're talking about like more complicated models, they might be thousands or millions of parameters.
Decide that.
See, those parameters represent your function, like the function that you want to fit. I'll talk a bit more about it when we move a bit further. But in the end, those parameters are like, they sort of construct that function. So imagine,
But I don't know what is the function.
that's the point. We want to try to find that function. We want to find those parameters. Those parameters will describe that function. So in the end, it's enough if you find those parameters. You can construct that function, and you apply that function to your data set. You can get predictions out of it. That's the point. So a simple example of machine learning is, let me go to the next slide. Yeah, linear regression. Have you guys done this at some point in your courses, like fitting a straight line to data, or even in your experiments? Okay. So linear regression is like the most simple example of machine learning you can think of, and you want to fit a straight line. For a training example, the model, you assume some values of phi 0 and phi 1, and you try to get an output as this. You assume some initial values for those parameters, and then you try to get a sort of prediction. And as I said, the loss is a measure of finding out how far away this prediction is from the true value. There are so many different losses you can use. Again, that depends on what kind of function you want to fit, how you want to model it. Least square loss is just one simple example. It's like, it's as simple as like, if you're trying to find the distance between 2 points, you use a sort of Pythagorean distance. You can think of it that way. There's also like a very good reason as to why least squares is used for regression, but I won't get into that. Is there okay, but yeah, so this is about linear regression. Okay, the figure that you see on the bottom right is, imagine you get that loss, and you plot that loss as a function of phi 0 and phi 1, which are the parameters you want to predict. And this is like a contour. So this is actually, because there are 2 parameters, this is a 3D parabola, and this is just a contour plot that's slicing that parabola at some plane, and you see this basically. So the ideal set of parameters which will describe that function correspond to where the loss is the least. You want to minimize this loss so that the predictions are close to the true values. And so ideally you want to find what is the minimum of this 3D parabola in this specific example. Yeah, okay. So here I have actually shown a couple of points on this parabola. Like if you take different values of phi 0 and phi 1, they will be on different points on this parabola, and those correspond to like potential functions you can come up with which can fit the data. For these sets of values, I have plotted some functions that you get, and yeah, you can see that for different values they do come up with different estimates of, or like different straight lines, and you want to fit a straight line that fits this data quite well. And to do this, we use a method called gradient descent. The idea of gradient descent is generally when you compute like, so gradient itself is like the direction of steepest ascent of a function. If you have like a multi-dimensional function, at any point if you compute the gradient, that tells you the direction where the function is increasing the most. In this case, you want to find the minimum of the function, so you want to go opposite to that direction. So the idea is, because this is a sort of, if you view it from like if you view a slice of this, it looks something like this, a parabola, and let's say you start from here, you want to find what this point is. Basically you use information about the direction of descent here, which is the slope here, which looks something like this. And then you want to move in this direction, but because this function is quite nonlinear and because the slope keeps changing at every point, The idea is that you take a small step, you move, let's say here for example, you compute the derivative once again, you take another small step and you compute the derivative once again, and so on. When you do this, there is a good chance that the smaller your step is, the closer that the final point you reach is the minimum. So when you take small steps, it moves in the direction of the minimum, and then in the end you reach the minimum. This is the whole idea of gradient descent. You take a point, you compute the direction of steepest descent at that point, and you try to compute, you try to move a small step in that direction, and you try to compute the minimum. Yeah.
What you directly calculate the stationary points derivative equals to 0?
Often you cannot. Like for a simple function like this, it's a 3D parabola, you can find it easily. Linear regression is one example where you can actually numerically or analytically solve for the stationary points. Often you will have like completely crazy loss functions. Could be like anything. It could have multiple minima, it could have saddle points, it could have all kinds of things, and often you cannot find an analytical expression for it. So yeah. So the idea is to move opposite to the direction of the steepest ascent, and
the same problem can be in gradient descent also.
The-
Suppose we are stuck in a local minima.
Yes.
There was a global minima.
Yes.
There, but gradient descent assures us that it will reach there in the global minima point. If
The-
it stuck in the local minima, then it's end there.
that is actually one of the issues. So I'll also talk about that a bit later. But yes, with gradient descent, that is one of the issues. You have to use some techniques, like for example, you have to change the step size, or you have to carefully choose where you start from, these kind of things.
But how can you know that for when you choose again?
That depends on your data set. Before you start doing these kinds of things, you need to understand the data quite well. Often you will be able to find patterns in your data which will give you motivation to have a good starting point.
It's a random data, completely random.
If it's completely random, try to know it first before starting this.
No, I mean like gas in ideal gas situation.
Okay.
Gas in box, the motion is completely random.
What do you want to fit?
Just giving examples, the data is this kind of random.
We know, for example, with ideal gases, we know a good deal about how they work, but also it depends specifically on what you want to fit. And yeah, you need to understand the data first before you make decisions about this. Yes, so gradient descent, as I said, yeah, you want to minimize and you want to set the gradients of the loss to 0. And the loss is the least square loss that is computed on every single point and then summed up. The derivative with respect of the loss with respect to the parameters phi1 and phi0, you can compute them here. In case of linear regression, as I said, it's an analytical problem, and so you can compute these derivatives directly. So once you have these derivatives, the goal is to then like take small steps and then try to fit it. You start with initial parameters, you compute the loss, you compute the gradients, and then you move the weights for a small step in the direction opposite to the gradient. And let me see if this video works. It's actually a video, but yes. So in this equation, you see this parameter called alpha. This parameter is called the learning rate, and that tells you how much in the direction of the gradient you want to move. So you have to carefully choose what alpha is. In some situations, choosing a small enough value of alpha already works. Sometimes you have to keep changing the value of alpha as you keep moving down the loss curve. Were you all able to watch the video? Did you watch the video? Like, that is supposed to be a video. I'm not sure if it worked. Okay, let me try again. Okay, so yeah, basically it is starting from a specific point, and For each point there, I'm also plotting the corresponding function that comes from it. And when I do gradient descent, this is kind of what it looks like. Here it's not moving that much because I kind of chose a good set of values to start from. But yeah, this is the idea of gradient descent. You start from a point and you take small steps in the direction of the gradient and you try to reach a minimum. Yes?
So learning rate constant throughout the input?
Sorry?
The learning rate?
Yes.
Is it constant throughout the input from the start to the end?
You can vary it. But yeah, it depends. Like in most real situations, yes, you need to vary it because often your data set is quite complicated and so the loss landscape you will get is pretty, like something like this, for example. And so you will have to vary it to make sure that it doesn't get stuck in local minima. Okay. But yes, as I was just saying, real life is quite non-linear. And often you cannot fit linear functions. Often you don't know, yeah, like in most situations you don't even know what you want to fit. And you want to find some relation in the data that you can then fit and make predictions out of it. Yeah, it could also be a very complicated function like this, for example. But like I said, you don't know this function beforehand and you need to find some way of fitting it. Also, another problem is that your data set could be quite large, in which case you could, like, even if it's a very simple linear regression problem, if your data set is really large, solving it analytically becomes a problem as well. With linear regression, for example, you can also formulate it as a problem of a set of equations, and you can try to do matrix inversion and try to solve the problem using simple linear algebra. But again, with linear algebra, matrix inversion is a very expensive operation, so you need to come up with other ways of finding the minima quite easily, and also something that scales up quite well. So we want to come up with a way of modeling, come up with a way of finding a framework which can fit nonlinear functions to any data set. And that is the idea of using neural networks. Have you all heard of neural networks? How many of you have worked with it or heard of it? Or okay. So yeah.
Also, like the last function that you showed, like from where did you get it?
This one. I think Gemini. I was like, oh yeah. So what I did was I told Gemini, consider the standard model, and based on that, give me an analytical expression for that. But why did you ask?
I thought it was like something actually it had some meaning.
I think it does have some meaning. This was just to show you that your function to fit can be quite complicated. But yeah. Okay, with neural networks, it's a computational framework that is used to model like nonlinear functions. The idea is that like you have some data, but you don't know what function you want to fit. So you take some crude representation of a nonlinear function and you continuously keep aggregating that function. Generally, it's called a composite function. Like if you have two functions, f of x and then g of x, you can create a composite function f of g of x. And if this, for example, is like some function, some simple function that you can build, some simple nonlinear function you can build, you can keep stacking this like continuously until it is quite complex enough that you can use it to represent your data. That's the basic idea of a neural network. Basically this idea of composite functions. But if you, for example, start with an idea of, say, like you saw the data previously, it was linear, and let's say you want to start with that, you want to use f and g as linear functions, and if you try to build this composition, you get this sort of expression, which is again linear in x. So the basic idea is that f and g, if they are linear functions, no matter how much you try, if you try stacking composite linear functions, you will still get a linear function of x. So in order to make this non-linear, there is this idea of an activation function. An activation function is basically a monotonically increasing non-linear function. Like in that plot, if you can see the green line, that is what happens when you take linear functions and keep stacking them together. The only sort of relation you can get from it is linear. Whereas if you use a monotonically increasing non-linear function like tan h, or like, this is called sigmoid by the way. If you use a tan h or a sigmoid activation function, it again increases monotonically, but the relation becomes quite non-linear. So the idea is to then take your data set, create some sort of linear combination out of it, and then add this activation function on top of it. This will give you a sort of non-linear function that you can start with. That's the whole idea of a neural network. The reason they sort of called it a neural network was because this is kind of something similar that happens in the neurons of your body. Like for example, I don't know fully, I don't know a lot about it, but the way I understand it is that if you, for example, smell something quite good, then like the not the olfactory, what is it for smell? I forgot. Like the smell receptors, it's olfactory. Okay, yeah. The olfactory receptors then get those like the odor molecules, and then certain neurons start getting activated in your body. Then impulses that go through those neurons become a little more stronger. The whole idea of like a neural network being called a neural network was that we have this sort of linear combination and then a non-linear activation, and that sort of activates a certain computational part of your data set. So when this happens, this means that the framework that you're using, that is the neural network, it understands some part of your data a little more, because of which when it does this linear combination plus non-linear activation, that part of the data set it is able to understand a bit better. So this idea of using a linear combination and a non-linear activation corresponds to one node of the neural network. So I've sort of highlighted it in red here. If you have like multiple inputs and you sort of linearly combine them, and then you sort of apply this non-linear activation function, you get some basis function that you can start with. This is just one node or one neuron in a neural network. Yes?
Why do you want the activation function to be
monotonically? The idea is that if it's monotonically increasing, so for example, if you take some feature in your data set, I don't know, like imagine there's a picture and you want to find a human face in it, and you feed it through a neural network. If it is able to identify, so if it is monotonically increasing, what it means is that it will consistently sort of get activated when there are certain features in the image. For example, if it's modeling, like if you're trying to capture what your head or your hair looks like in an image, what happens is that when an image is being fed through a neural network, that specific part of the image which like a specific neuron or like the specific computational unit sees, if it is linear, it consistently picks those parts, and so it can identify those parts quite well.
When is just model in monotonic increasing? Because your linear functions are increasing and your activations are also increasing. So when there's a model increasing?
So if it is not monotonically increasing, like I said, if you want to model a specific part of your data set, it is possible that the weights or like the nodes in your neural network which are responsible for seeing that part of your data set don't get activated, which means that information about that specific part is not passed on to the later layers, which means that your loss may not be accurate. So this might happen, yes. That's why you want to always keep it linearly, like monotonically increasing.
My understanding is it can be monotonic. Is the
Sorry?
It can be monotonically decreasing or increasing, but it should be monotonic. That's what I understand.
It is monotonic, yes, but generally if it's decreasing, what happens is, I mean, like if your neural network has multiple layers, if it's decreasing, your weights will immediately go to 0, or like if you compute the forward pass of the network, I'll talk a bit more about that, but when you do that, the activations will go to 0 quickly, because of which in the end you won't be able to model it accurately.
And then it also converges to 1.
Yeah, it's dying.
Yes. Okay, sigmoid and tangents, yes.
For large extent.
Yes, yes.
Dimension gradient.
Yes, yeah.
That's okay.
So it's only valid in that region only.
This is actually just an example. Like there are some activation functions which don't die off at 1, for example.
This exponential function is very monotonically increasing function. Why don't we use it?
Then you will run into some other problems, like for example the vanishing gradient you were talking about. What can happen is that when you're using exponential, your whatever computations come out of it blow up like anything. So then again, then it'll reach a stage where you can't accurately model it anymore. There are like specific reasons why, for example, sigmoid goes from -1 to 1, and even tanh, for example. There is also another function called ReLU, which is like 0 for negative values and then linearly increases for positive values. There's all different kinds of activation functions, and they all have slightly different purposes. Okay, let's see. Okay, so like when you have a neural network, there is this idea of a forward pass, which is basically like when you had linear regression, you had 2 parameters, you just compute phi 0 plus phi 1 x, which is like the prediction of the network, the prediction of the linear regression problem. In this case, forward pass is basically what you get from the network when you're trying to predict. So here there are a bunch of different things. Suppose you start with like one value of x, like you did in the linear regression problem. This is kind of what it looks like in the linear regression problem. You have 2 parameters you want to fit. But here, for example, in this sort of neural network, there are 3 nodes in between. So what is happening is each of those nodes is like one set of linear combination and a non-linear activation function. So from the first input, you compute this sort of theta 10 plus theta 11x, and because there are 3 nodes, so yeah, like you start with this and then you compute this non-linear activation, and because there are 3 nodes, you do the same thing 3 times, and then you sort of take these outputs and then you try to get another final output based on these outputs. So the idea here is that these three outputs that you get, H1, H2 and H3, these are your sort of non-linear, simplified non-linear functions that you get. You want to try to make them more complicated, so complicated in the sense complex enough that they can fit your data quite well, and so you sort of combine them to get a sort of final output as well. And here in this case you want a function f that is a function of x and all of these parameters. There are like 6 parameters here and then like 4 parameters there, and in the end the idea is that these 10 parameters completely represent the function that you're trying to fit. So you want to find these parameters. Once you find these parameters, you can simply do a forward pass and then get a prediction of that function. So this is the idea, and there is this idea called the universal approximation theorem, which is that you can take any data set, and you can it could be any data set with any sort of relations between the data set, and the idea of the approximation theorem is that you can take any neural network, any appropriate neural network, and that neural network can be used to model this data set, and this can be done to arbitrary precision. So if, for example, if you have, if you again take the example of like large language models, they have like billions of parameters. They are trained on the entire internet, and in the end they do output a lot of things. But the general idea is that you can take this to any level of complexity, to any data set, and you can find an arbitrary neural network which will in the end produce like a function which can capture the patterns in this data set, and that can be done to arbitrary precision. This is actually one of the strengths of a neural network, and as I'll talk about a bit later, it's also one of the flaws. Yeah, go ahead. That is the exact problem. Like often there may not be any pattern, but a neural network will still fit something to it. Like imagine you have, I don't know, like a two-dimensional data set with just random points here and there. Imagine there is no relation between these points. A neural network will still try to do something like this. It may not mean anything, but it can still find some way of fitting this function. That is also one of its, like, it can be a strength, but it can also be a huge flaw. And yeah, I'll actually talk about that in a bit.
One hidden layer minimum, right, for this to hold?
Actually, you just need one hidden layer for this. With just one hidden layer, you can model anything. But of course, like with one hidden layer, you need like so many number of neurons in that layer. But yeah, I mean, that's why people come up with different sorts of. I don't think there's a requirement on the minimum, but it is that like you can take any number of neurons, you can find some number of neurons that can fit your data set. There's no restriction on the minimum. Okay. So after this, yeah, it's the same process. Like previously in linear regression, we had this idea of gradient descent. You have a lost landscape, you're trying to move in the direction of the opposite to the direction of the gradient to find the minimum. It's the same process here. Like you want to, those 10 weights that you see there, you want to compute the gradients of those weights, and you want to move the weights in the direction in which they decrease a lot. You can directly compute the derivatives of the loss with respect to these weights, but there are more, like there is a more sort of accurate, not accurate, but like a more computationally efficient way of doing it. Because for example, if you take this gradient, for example, the partial derivative of loss with respect to, let's say phi 2, this was, if you remember from the previous slide, this was something like the prediction from the network was something like what was it, phi 0 plus phi 1 h1 plus phi 2 h2 plus phi 3 h3. So the derivative of the partial derivative of it with this is just h2. So for the outer layers, for the outer layer, you can directly compute these partial derivatives because you know what these functions are when you do the forward pass. For the other ones, for the parameters that are more inside the neural network, you can find them, but you need to use the chain rule of differentiation because, for example, you can find this derivative, and then this derivative then is required to compute the derivatives of the loss with respect to theta 21, theta 20, all of the parameters which lead to h2, for example. So you can compute these derivatives directly, but one like better way of doing it is that you start by computing the gradients on the last layer, and then you progressively move inwards, because like when you compute the gradients of the last layer, they are then used to compute the gradients in the first layer, because the gradients in the first layer depend on those in the last layer. So you can compute the gradients in the last layer, store them in memory, and then move to the previous layers and then try to compute those derivatives. This idea is called backpropagation because you're moving from the prediction, from the loss, you're computing the first gradients and then you're moving backwards. Yeah, it's the same thing. So you basically use the chain rule of differentiation. When you do backpropagation, because you use the chain rule, and these are basically h1, h2 and h3 are nonlinear functions for which you know expressions. So you can actually exactly compute these gradients when you move behind, like backwards. For example, yeah, like you start with those weights and then you compute the derivatives and you use those derivatives to compute the derivatives of the loss with respect to the weights in the first layer. And yeah, once you have all of those derivatives, you use them to then update the weights. And you basically keep doing this process iteratively. You take a small step, you try to compute the forward pass of the network, then you compute the loss, then you start by computing the derivatives one by one. And once you reach back to the input, you have all the derivatives, and then you use all of those derivatives to update the weights. So it's the same idea as linear regression, but because you're trying to model a nonlinear function, there's some complexity involved in this. I also wanted to show you one example of what it looks like to train a neural network. I want to fit a simple function, say the exoplanet orbital period and the semi-major axis relationship. This is like so generally when you want to train neural networks, there are a lot of these standard libraries which abstract away a lot of things. For example, in PyTorch, you just have to write a few lines to like build a neural network. You just write one function for a forward pass which is basically like 1 or 2 lines of code, and that thing does all of the computation for you, the forward pass and also the backward pass. And because this is like a nonlinear, a neural network is used to model a nonlinear function, it still does help if you can simplify wherever possible. For example, in this case, if I remember correctly, the square of the orbital period is proportional to the cube of the semi-major axis, if I'm not wrong. But you can still, for example, use the logarithms of both these quantities and then still try to fit a linear function to it. And in that case, your neural network will function much better. So this is this idea of feature scaling and like standardization of your data set. When you do these things, your network learns quite well, and it also doesn't run into numerical errors. So this is the general idea of like simplifying wherever possible. And additionally, you also want to use as much data as possible to prevent overfitting. That's where I mentioned this, where if there's like no pattern in the data set, it'll just keep fitting whatever it wants. So when you know something about the data set, or when you have a lot of data, and when you try to fit to this data, it will try to learn general patterns in the data set but not the noise. So that's why you want to avoid overfitting as much as possible, because you can, when you take a neural network, you can keep going you can try to add as many nodes as possible, you can try to make it as complicated as possible, and it will fit the data quite well. But you also want the fit to be such that it learns general patterns in the data set, so that you can then use it to make accurate predictions. Yes, you had a question?
How many data points are enough to not having overfitting for an application? Is there any?
There is, again, no, it really depends on the data set. So typically what people do is, if you have some data set, you start with trying to understand your data as much as possible. That's where, for example, you find out which initial point do I start from, so that it trains fast. What kind of initialization should I do? There, for example, you can try to get a sense of how your neural network is behaving by, for example, you take some configuration of your neural network, and the configuration is such that you try to first overfit the data. That way you know that it is actually fitting, it is actually an overkill. So then you start removing some like components from the neural network, or you can start with a very small data set. Yeah, you start with a small data set and like a complicated neural network, and you try to overfit, and then you slowly remove components one by one, and then see where it is getting a more general fit. So that's the basic idea.
Using more data, make it more susceptible to learning the noise also. Like sometimes we stop the training process, right, to prevent overfitting.
Sometimes, yes, yeah.
Yeah. So using more data means giving it more noise to learn. Isn't it like kind of?
Yeah, the general idea is that if you give more data, it will try to learn like the patterns in the data. But if your data, for example, is if you are collecting data from like a wide variety of sources, they will all have their own intrinsic noise. And so when you try to make the neural network fit to the data, it will struggle a bit more because there's like all sources of noise which it doesn't know what to do with. If you just pick like a very simple, very small data set, or like a data set which belongs to a very specific source, it will quickly sort of learn what the data is, and it will also try to sort of memorize what the data is. So then it will do all of the random overfitting. It really depends on the
Because overfitting depends on the data, number of data points or the number of iterations.
Both actually. So
The more data is more beneficial. So why should I restrict myself to have less amount of data? More data is obviously good.
more data is beneficial. See, overfitting happens because of.
I understand there is more noise included in it. Okay, but I will then do a less number of iterations so that it does not overfit the noise. Overfit the data and learn the noise.
Then it is also possible you are not learning the general pattern in the data that you want to learn.
Sufficient approximation.
So that's the thing. So like there's lots of factors which determine this. It depends on what your data is. It depends on how diverse your data is, how big it is. It depends on what kind of configuration you want to start with for the neural network. It's an iterative process. Like you have to choose some configurations, try to train it for a while, see if it works, and then before you start training, you try to understand your data as much as possible. You might find some things about the data. You could use that information to sort of then decide what parameters in the configuration you want to change, so that then it gets to a more better fit. So there's all sorts of things you can do there to try to improve the fit. So yeah, this was another. Okay, yeah. So I think this is actually another video. Let's see if it works. This was the problem that I showed you about the semi-major axis in the orbital period, and I used a neural network to. In the end, it is fitting a linear function, but because I used a tan H activation, or like one of those tan H or sigmoid activations, and so when you saw how it started as a sort of linear combination of that activation function, and then as you keep progressing with the training, you get more and more epochs, and then it tries to understand the data better, and then it tries to fit it better. But so as a couple of you asked, a neural network can do this sort of fitting quite well, but that is also its biggest flaw. So I saw this quote, "Neural nets are a leaky abstraction," by this person called Andrej Karpathy. He is one of the big names in the field of AI, I would say, and he has this blog called "A Recipe for Training Neural Networks." It's actually quite a nice blog. If you are looking to, if you are at any point training a machine learning model, it's quite a good blog to look at. It is quite, I think, 5-6 years old now, so it's maybe some things are outdated, but it's still a very good starting point, I would say. So this is about linear regression, and then non-linear, like fitting a non-linear function to a data set, and this was basically the fundamental idea of machine learning. I have a summary so far here. If If you have any questions, I'll pause and I'll take them now. Are there any questions? Yes.
Just we have one doubt. The y-x curve they are made on the black hole. Can your ML model give a plot like that where 1x gives you y?
Which one are you talking about? This one or that one?
No, the y-x plot.
This one.
Yeah.
Okay. What was the question?
Is it possible to extract from your mathematical ML model that will give you two values of y for 1x?
Yeah, I would say it is possible, yes. I mean, it's possible, but yeah, it depends on your data set and the model. Like, this is actually just noise. There is no statistical pattern in this or correlation in this that you want to find out. So it can do anything to try and fit.
If it's like multi-level classification and all of that, it can be multiple answers, right, for a single.
Yes.
Multi-label classification, yes, I think so, yeah.
It will mostly for multi-classification, it will give you probability solution as to what is the probability of this versus that class. And it cannot have a defined probability for something.
So
Yeah.
will that probability be continuous? I think we have two values, two distinct values of y in this curve. Will it be a continuous curve as in
Yes, it will be continuous. Okay. Any other questions? Yes.
And I think what the next topic is NeuralODes.
Yes. Okay.
Can it cross its solutions? It can just do anything. Suppose I don't know the physics,
Okay.
okay, and it does the right thing.
Yeah.
Okay. Now I know the physics, so I'm validating it. Okay. But sometimes unknown physics area, and it does a thing. Can it cross its solution?
Define trust.
Depends on the model.
Yeah, it depends on the model. It depends on the problem you have. Like, for example, you might be having a complex problem where you're doing a lot of different modeling, and then there is one component where there's two variables and you don't know the relationship between them, but you have data about them. You can, for example, fit a neural network to relate this data. What you want to do with that fit depends on like how important that fit is for you. Is it just like some set of parameters you don't care about, and so you just fit it to like help you with modeling other things, or is it something you really care about? And if it is something you really care about, I mean, in the end, neural networks are like just statistical fits. They don't tell much about what the fit is.
Understand what's happening. You don't understand the physics or the science or the understanding of the thing it's happening.
By default, no, it doesn't.
Just numbers.
It just fits. Yes, it just looks for patterns based on what is there in the data and tries to fit them. Yeah.
Like all the ChatGPT stuff and all of that isn't really
ChatGPT. What about ChatGPT are you talking about?
like, it's just a fit, right? It just finds the next word in the sequence.
Yeah.
That's all it is.
Yes.
So,
Yeah. ChatGPT, for example, is trained on the entire internet, so it has seen a lot of data. It has seen a lot of patterns. They also do like multiple different kinds of techniques to make the responses more streamlined. So in the end, yes, it has seen a lot of information, and like the information that the outputs that it provides are good enough, I would say, for a lot of different purposes. I mean, of course, you've also seen AI hallucinate, and that is also actually an active area of research. Like, people are not fully clear why that happens.
this question was the same as like if I don't know coding but I use a no-code platform, like does it really understand what code does, or does it know what comes next after this? Like print F is the bracket. Does it really know like what the coding does, or does it just know okay after this should come? Statistical.
It's just statistical. It has seen a lot of things like that, so it knows what comes next. Something like that, I would say. You can so NeuralODes, for example, that I will talk about, is a way of incorporating a physical model into a neural network. There are other ways of doing that as well. When you actually incorporate physics into a neural network, it can provide better fits. It can it still doesn't really understand your data, but it can help you reason about what the fit it provides is, and it can just provide general, like better fits in general. Okay, so this is a summary of machine learning, like classical machine learning. So far we saw that the data that we were using was more, so if you have a set of points as a data set, you have like y and x like this. You have a bunch of different points in your data. You can sort of swap the points, like you can, if it's like a vector, if you have like a vector y and a vector x, and y corresponds, like the first position of x corresponds to the first position of y, and they are all related to each other. You can sort of swap x and y for the most part. Like if you generally shuffle this, and then if you swap the positions of one of the points in both x and y, and then if you like train a neural network on it and try to make a prediction from it, it'll most likely give you the exact same prediction. And so there is sort of, here there is no time dependence really, in the sense that like one point, the input of, or the output of one point doesn't really depend on the output of some other point. And this becomes important in like physical systems where you have some function that's dependent on some parameters which evolve with time. In such a situation, you can use like classical neural networks, but what would happen, for example, is if you have like a, I don't know, like a sine wave. Imagine your data is like this, like it's on a sine wave, and then suppose you want to fit a sine wave to this. Suppose you have data from 0 to, I don't know, let's say 3, it doesn't matter. Like let's say you have data only up to this. Your neural network will, it will like understand the data quite well, and it will try to produce this curve which fits the data quite well. But then if you try to go beyond this, and then if you have data like this, your neural network might produce nonsense. So you want to sort of capture this time dependence as well, so that this can be used to model physical systems. And that was the general idea of like, time dependence in general. And typically, like when you have physical systems, they might be modeled using ODEs, and like generally you can represent an ODE this way. And like you can sort of discretize this. You can try to get oh, there should be a delta t there. I forgot that. But so you can try to sort of discretize an ODE. By discretization, you're basically like breaking it down, like breaking time into like small chunks, and then slowly computing what the next step in the ODE is, and so on. In this way, you sort of have a relation where like every point depends on the previous points in some way, and you want to sort of capture this dependence. And also another thing is that, for example, here you had, in this example, you for example had just one set of points, and like they had x and y values, and you're trying to predict y. It might happen that, for example, you might have multiple such curves of different forms, and you want to fit all of them simultaneously. So in that kind of a situation, you will have multiple input vectors, and those are like different features of your data, and you want to fit all of them simultaneously. And you also want to understand the time dependence in those features. So for this kind of a situation, neural networks they can fit up to a certain point, but then if you have more generalized data, it can be much harder. Yeah, so one example of that is this. I'll talk about this plot a bit more later, but this is like an example of abundances of chemical species, and then on the x-axis you have something called visual extinction, which is like a way of knowing how deep you are in a molecular cloud. I'll talk a bit more about this plot later, but this plot is just, you get this plot from just one set of initial conditions. There's 3 variables that I used, for example, and I set those 3 variables to some initial values, and then based on that, if you try to evolve this set of ODE or like a set of ODEs, you get this kind of a plot, and it's you want to sort of capture the time dependence in this plot, and because that was only for like one set of initial conditions, you also want to understand how this will vary for different sets of initial conditions. And those different initial conditions can be from a really large parameter space, like spanning many orders of magnitude. So in those kind of situations, you need to sort of incorporate this time dynamics into your neural network, and that's the idea of a neural ODE. Yes, so like if you have linear regression, in linear regression you had like one value of x relating, one value of y relating to one value of x. Now you have like one set of initial conditions, and that leads to like multiple different vectors, all of which depend on time. So you want to model all of them simultaneously and understand their time dependence. I'll briefly talk about numerical ODE solvers, just so you get the idea of how, like if you're not exposed to ODEs, you get an idea of how people solve ODEs. So for a general ODE, you can typically represent an ODE this way. You have a dependent variable y that depends on time, and this quantity f of t and y, that's called a vector field because it tells you how the direction, or like how y changes with respect to t. And yeah, if you want, so like generally if you have a very simple equation, you can integrate it, you can even find an analytical solution for it, but often you cannot find a solution analytically, and so people resort to numerical techniques. Like generally all numerical techniques involve some sort of discretization. So as I showed previously, you just take this and then you try to sort of relate this so that the previous point can be the next point can be computed from the previous point using the function and by moving your time step by a small amount. This method is actually called Euler's method. It was one of the first methods, I think, that was used to compute solutions of ODEs. But as you can see in that plot, what happens is that when you use Euler's method, you start getting, you do get like solution points, but they slowly start diverging from the actual solution. Here what you are doing is you are at a particular point, you compute you know the gradient of the vector field at that point, and so you use that to sort of move it by a small amount and then take the next step. But yeah, as you keep moving further, it sort of diverges away from the original solution. And so there are some better methods for that. There's something called RK4. What RK4 does is it goes to a, like, instead of just taking the derivative there, it takes like estimates of 4 derivatives. I think it's like at that point, and then somewhere in between it takes 2 derivatives. I don't know the exact expression on top of my head, but like it computes 4 derivatives at 4 different points, and it takes a weighted average of that, and then it tries to produce a more accurate solution. So it's like a different form of discretization, but in the end you discretize the equation, you take a small time step, you compute some estimate of what the next time steps solution should look like, and then and then you try to progress with the solution. So with this, yes?
So if my understanding is not wrong, neural ODEs basically we're trying to use a neural network to learn the solution to an ODE.
Yes, it learns, yes, so I'll come to that. Like it learns solutions to an ODEs, and it learns the dynamics of how this system depends on time. And so you can then use it to, you can do a lot of things with it actually. But yeah, I'll come to that. I'm going to talk about neural ODEs now. So yeah, you take the same ODE from before, but like yeah, we don't know what the vector field is, and that's what we want to fit to. You take this ODE and then you make the idea of a neural ODE. The fundamental idea is that you make it predict, you make a neural network predict this function. So then this f has parameters theta, and you want to try to find the parameters that then fit this function. And so this is a very neat like idea where you sort of take an ODE solver and you wrap it inside a neural network. You give an input and then you do an ODE solve. This ODE solve is sort of in like a higher dimension. For example, if you take this example, if you have like an entire data set that looks where each point or like each entry looks something like this, I think like I don't know, if you're taking like let's say 3 such curves, and then you take like I don't know 200 time steps, and if you have 20 such examples, it will be these many points. So this output that you get from this particular block would be of those dimensions. But in the end, it's a neural network and you have a loss in the neural network. So you want like one set of predictions from it, and you want those predictions to be of the same dimensions of the input so that you can compute the loss. So you do these sort of transformations, affine and linear transformations, to sort of bring it down to a lower dimension where the output matches the dimensions of the inputs, and then you compute the loss. With this, there are actually several benefits. One is that yeah, it learns continuous time dynamics without knowing what that function is. So it learns the function and then it also learns the dynamics of how the system would evolve. And yeah, you can model it to arbitrary precision. If you consider this example, you could, for example, take fixed time steps, here, whatever, like for example, and yeah, I mean, normally if you use an ODE solver, you can set a fixed time step to it and it will evolve that system at those time steps. But with a neural ODE, what you can do is you can also take sort of what we call stiff equations or like stiff systems. For those kind of systems, you need more advanced ODE solvers which modify the time step according to what the dynamics looks like. You can also wrap that kind of an ODE solver, a stiff ODE solver, into this, and the neural network will learn those dynamics as well, because in the end a neural network is a universal approximator. And so this is a very nice way of the network to learn very non-linear stiff systems dynamics as well. It also generalizes well to future like time steps, like I was talking about when like imagine you had like 3 inputs here. These inputs would have like I don't know specific initial values x0, y0, z0, whatever. These inputs, imagine they are sampled from like a parameter space. This would be a 3-dimensional parameter space. You would need lots of different points to like sample that parameter space quite well, and so each of those points would correspond to a different set of initial conditions. And in a 3-dimensional, like if you keep going to higher dimensions, you need to sample more and more points in order to like understand that parameter space quite well. A neural ODE gives you a way of understanding the dynamics in a higher dimensional space quite well, and it also helps you understand the dynamics to arbitrary precision, because you can use a stiff ODE solver. And yeah, of course, depending on the situation, because it's a neural network computations are pretty optimized at this point. I would say if you take standard libraries like PyTorch or JAX, they are really quite well optimized to make neural network computations. And because of that, in certain situations, you can get really, really fast predictions from a neural network, from a neural ODE. And the way you train it is kind of similar to like the same idea basically. You do gradient descent and you do backpropagation. But a small catch here is that you have to, because you have an ODE solver in the neural network, that ODE solver also has computations where, like, there's one computation and then there's another computation based on that, and there's multiple computations. So when you are trying to find how the loss varies with respect to all of the parameters in those computations, you need to sort of do backpropagation through the ODE solver as well. So if you take this simple like Euler example, you need to compute the loss, the derivatives of the loss with respect to these points as well. And this would involve some way of, taking the loss computing derivatives and propagating them through the ODE solver. Now, a lot of the numerical ODE solvers you see, like for example, if you've used SciPy's ODE int, it has an ODE solver, but it does not have a way of computing derivatives while it is solving, or like using the information while it is solving to compute derivatives. So that is actually an idea of what we call automatic differentiation, which is the idea of, like, if you are doing a computation, you want to find arbitrary derivatives with respect to the parameters in that computation. So you need your ODE solver to support that idea of computing derivatives through the ODE solver. There are specific libraries which do, so yeah, like automatic differentiation does this, and like there are specific ODE solvers which have this ability to compute derivatives in between, and these are called differentiable ODE solvers. There are like standard libraries like PyTorch and JAX based libraries which do that. I am actually a fan of JAX and diffrax because I used it in my master's project, and it was way better than PyTorch. Specifically for NeuralODE modeling, it was way better than PyTorch. I'm not sure if you've used any of these. Like PyTorch is in general quite good for a lot of things, but I found that it was a bit bad compared to JAX for NeuralODEs. Better as in, so JAX is actually optimized for some kinds of vector operations. You can do like multiple different kinds of vectorization that you can't do in PyTorch.
Pretty much anything in PyTorch, right?
Sorry?
In PyTorch.
Mm-hmm.
It is pretty good.
It is pretty good, but I think in JAX they have these sort of specific kernels which, for doing specific kinds of vectorization, they are optimized for those. And I'm not sure why. Like, actually, the first the first paper of NeuralODEs, when it was published, they released a library called TorchDiffEq, which is a PyTorch based library. I think it was released like 5-6 years ago, and I don't know why, but still their support is not that good, like in comparison to JAX. JAX was more recently developed, and diffrax was actually written by a person who did a PhD thesis on NeuralODEs, and like his PhD thesis is sort of the gold standard for NeuralODEs now. It's a very good book, and he was the one who wrote this library called diffrax and a bunch of other libraries based on JAX. And for some reason, I find them to be much more better than. I started with JAX, yes. Like for this, okay, so I'll show you this in the next slide. I'll show you like a training loop for NeuralODEs. So this is a specific set of equations that I chose. This is just a random, like a prey-predator dynamical modeling equation. Like it is a periodic equation, and so I thought it's a good idea to try and fit a NeuralODE to this. I actually trained this on my CPU itself with JAX, and it took like half an hour to 1 hour. With PyTorch, I trained it for like many hours, and it didn't finish training in the end. So I don't know the specifics about that, but I have found that it's better there. So I took the specific example of a dynamical modeling equation, and I passed a few parameters, which is like the time and then those alpha, beta, gamma, delta parameters. I set them to fixed values, and then I passed them as initial parameters. And I also set initial conditions for the populations of the prey and the predator in this. And then I tried training this, and let's see if this plays. Okay, yeah, it plays. So if you do a typical, if you take a simple neural network, It's very likely that it will struggle a lot to get those periodic variations. I mean, you can use an extremely complicated neural network with lots of nodes and layers, and it might still model it, but like I said, it may not capture the time dependence well. So yeah, I trained this with the JAX-based library, and yeah, I mean, so one thing is that NeuralODEs are generally difficult to train because you want them to capture the statistical patterns in the data as well as the time dependence in the data. So there are actually a bunch of techniques that people use to train NeuralODEs. One thing that I used, for example, was here I sort of took only, for example, up to the first 5 time steps in one epoch, and then I trained that for like 100 iterations, and then after 100 iterations I started taking this data like this up to this time step, and then I trained that for another 100 iterations, and so I slowly introduced data into it so that at least for the first 100 time steps it can model this part of the network quite well, and then when you introduce more data there is some discrepancy in the modeling here, but then in those 100 iterations it picks up this part of the curve quite well. So there are some sorts of techniques like that you can use to try to get good models, but yeah, the general reason why it's difficult is because, as I was mentioning, there are so many different parameter values, initial parameter values you can choose. You might have to sample from a very high dimensional space to get those parameter values. There's also like lots of different features. Like one curve here is like one feature, for example. You might have a situation where you have to solve for so many different features simultaneously. So there's all of these problems with NeuralODEs, but I think libraries like JAX make it a bit easier.
Can you replay the...
Let's see. Okay. I took snapshots at every 100 epochs, so yeah.
Introduce data points every 200.
Yeah, something like that. Yeah, I don't remember the exact number, but yeah, like after a fixed number of epochs, I started introducing more and more data. Because also it's because we're trying to model a time-dependent system. If you take a smaller period of time and like force the network to learn the dynamics in that specific period of time for some time, it picks up those dynamics well, and so for the next set of points it already has a good starting point to start with. So yeah, that was the idea behind it. Okay, and then let's see. Okay, so this is the idea of NeuralODEs. Does anybody have any questions? Yes.
So the graph on the left, is it just the training wala?
The graph on the left is the fit actually. So at every point you get y and x as a function of time and you plot them.
You trained it and then you got something like that.
Yeah.
And then did you test it now?
In this specific example, I did not test it, but generally you should test it, yeah. This was just to show you how they fit, that's all.
I'm a bit confused about NeuralODEs. So
Okay.
are we training it to predict the trajectory or predict the gradient at every point, and then use an ODE solver to solve the trajectory?
So that's the entire setup of the ODE solver and the neural network around it. It is in the end giving you the final like dynamics of this, the final x and y variation as a function of time. The ODE solve the neural network, which is basically okay, wait, I'll show you this. Where's the okay? So the neural network that's representing this, like that learns the derivative, and then when you wrap the entire system, that in the end gives you the final dynamics. Does that make sense?
So then, how does so the inputs are the initial conditions?
The inputs are the initial conditions, time, and some other parameters that might describe the ODE. Yes.
Okay, and then the output is that's the gradient.
No, the output is the final, like how much ever you evolve the system after some time.
So it's like the dy by dt is the output.
The integral of that is the output.
Okay. y is there.
Yes. So if you have like x and y as a function of t, if you feed time, you get the final. So see. So let's say the inputs are like t, x, x0, y0, alpha, beta, whatever. You feed this into the neural network. In the end, you get some like x of t, y of t at some, okay, let this be capital T. At some t. In the end, this is what you get. The computation of the vector field, which is the f theta of x, y, blah, 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 that's happening somewhere in between. And then based on that, it is computing these.
So what we take it down, like what is the data we
You need data, it depends. I mean, so you need data of, so if you are trying to find, like predict x and y as a function of t, you need data of x and y, like you start at different initial conditions and you have like x and y. This is for like one set of initial conditions. Imagine you had another set of vectors like this for a different set of initial conditions. You will have like an entire data set of these sorts of inputs.
So training like a set of simpler equations.
Can you say that again?
Are there like sets of simpler equations that our model has to solve and we know the solution of? So we can.
The model doesn't know any equation. It is approximating this part of the derivative of the equation. It approximates that and it gives a prediction. Then you do the same, like the loss computation and iterating it so that, yeah, you get a better prediction.
What is the difference between like the small t given an input and the capital T output?
So this is like, so you imagine you have data points like initial conditions and then you evolve the system so that you find the values of these points at some other time t. Like let's say this is t. So it takes these initial conditions and it gives these outputs.
What is the small t?
Small, it's just time, like the variable time.
And the capital T is the value.
It's some,
value of time that we get.
yeah, at some value of time where you want an output from it.
Computationally more better than just using, let's say, RK.
It is computationally more expensive, but the difference is that when you're using RK4, you know what equation it is. You know f theta, basically. Here you don't know that f. You just have data. You know there is some time-dependent modeling there. You want to find out what that is.
like over here, you have only used like the first order equation, like first order derivative, like that. If you have higher order derivatives,
Normally, if you have higher order equations, you can split, like if you have an nth order equation, you can split it into n first order equations and solve them simultaneously. You can do a change of variables and express them as n first order equations. Actually, all numerical solvers do work that way. If you feed it an nth order equation, that's what they do. Okay, any other questions? Okay, with this background, I'll start talking about the astronomy part now. Let me go back to this. Okay, so I'll talk about photodissociation regions, emulators, their applications. What time is it? Am I running late? Oh wait, yeah, it's 6:40. Okay. Okay. Let's see. So with photodissociation regions, okay, let me start with this picture of the Orion Nebula. Does everybody have a physics/astronomy background? Can I understand? Do you guys know what a nebula is? Just so I am fully aware of the background. That's a no. Okay, so a nebula is there are different kinds of nebula, but generally it's like a region of hot gas. And in this specific case, Orion Nebula is a place where there's a lot of star formation happening, because there's like a cluster of stars here, like they are very hot stars, and they heat up the gas around it, and that leads to a lot of different like physics, and in the end you have a sort of environment where you can form stars. So I'll start with this picture, and if I zoom in on the middle part, that's where I talked about where there are like hot stars in between, and the star heats up the gas around it. And what happens because of that is that you have a sort of layered structure where when the star is heating up the gas that's close to the star is ionized, but when you move far away from it, it's either atomic or molecular, and like the temperature reduces. And so it leads to like multiple sorts of transition zones, and this region is called so that is the cluster of stars, and this region where there's a lot of different chemistry happening is known as a photodissociation region. It's called a photodissociation region because the central hot stars produce a lot of UV photons, and these UV photons ionize the gases around it, and that leads to a lot of photochemistry. This is basically a schematic of what a photodissociation region looks like. You have a lot of different like atoms and molecules there, and depending on the ionization energies of those atoms and molecules, you get different sorts of transition zones. Initially you have this sort of H and H2 transition zone, and then as you move further into the PDR, you have C plus turning into C, and then CO, and then oxygen turning into diatomic oxygen. Here is where there is this quantity called visual extinction, which tells you how much radiation is absorbed as you move inside the PDR. So it can typically be represented through the population of hydrogen in the PDR, and because the more you go inside, the more the radiation gets attenuated. And so there's a bunch of different like physical variables which tell you what a PDR looks, which help you understand how a PDR can be modeled. The radiation field, that is the total amount of radiation that comes from the star, and it gets absorbed as you move inside the PDR. There's the gas density of atomic hydrogen that you can use as a proxy for the radiation field as well. And if the PDR has a lot of hydrogen, then there's more absorption and attenuation happening. And then there is, when you have cosmic rays hitting the PDR, they ionize the gases, and then also you have like molecular species turning into like ionic species, because cosmic rays cause that sort of dissociation. And there are so many different species, and there is this database called the UMIS database, which is like a collection of all the different chemical species they found in space, and like all of the different sort of chemical dynamics that goes along with that. It's a pretty huge database, and like they found all kinds of like elements in the periodic table in different sorts of environments. It's quite interesting. So that's this whole field of astrochemistry, where you use chemical molecules and atoms to describe physical processes. So there's two different things, like this thermal and chemical balance in PDRs. There are a bunch of different heating processes, mainly photoelectric effect on dust grains, and cosmic rays, because they dissociate, they also cause a lot of heating. There are also cooling processes, which is mainly because of collisional excitation. When you have like atoms colliding, they might move to higher energy states, and when they decay down to their lower energy states, that releases radiation, and because of that they cool down. Generally, when all of these processes contribute to the chemistry in PDRs, and generally you have all different kinds of equations happening, and you can sort of try to find out the dynamics of those equations. For a simple equation like this, you can try to find out the rate of formation of AB2, and that can be represented in terms of the individual variables. You have these rate constants which determine the rate of formation of those elements. It turns out that those rate constants depend on temperature, and so in the end, how these chemical species the dynamics of these chemical species then depends on temperature and all of the thermal balance and the thermodynamic processes happening. So typically when you model PDRs, they are steady state and depth dependent models because these are fully formed molecular clouds. They've undergone evolution for like millions of years, and in the end they've reached a sort of equilibrium state where the abundances of molecules and the temperatures vary as a function of depth or location in the PDR. So typically you can take like initial abundances of chemical species, you can choose a geometry 1D or 3D, and then some of those physical parameters that I talked about, like dust grain properties, rates of chemical reactions, you can take them as like initial conditions, and then you solve the chemical kinetics for each species. It's basically ODE solving, and you try to get the dynamics of those chemical species as a function of location in the PDR. You can also try to understand how the temperature varies because of these dynamics. So this is typically what an example of that looks like. On the y-axis is visual extinction. On the y-axis is abundances as a function of visual extinction. These abundances are typically expressed as a fraction of like hydrogen abundances. And you can see different species behave in different ways. Like if it's molecular, then you know that the abundances of molecules increase further as you move into the PDR because radiation gets attenuated so they don't get dissociated. Closer to the stars, like in front of the PDR at low visual extinctions, you have more atoms and concentration, like a larger concentration of atoms and ions. And there's so many different computational models of PDRs, and there's an entire paper that talks about how you benchmark these PDRs, and they all have they're largely similar, but they have minor variations, and they're all used for different modeling different regions of the interstellar medium, let's say. So when you have, okay, so you can choose for this sort of an example, as I was talking about, this corresponds to one set of initial conditions, and this is one set of initial conditions of these three parameters: the radiation field, hydrogen concentration, and cosmic ray ionization rate. You can choose multiple different sets of initial conditions, and this will give you a sort of model grid where you use these initial conditions and you evolve them as a function of visual extinction, and that tells you what the chemical dynamics looks like in a specific PDR. But yes, there are a bunch of different issues, or in the sense, more than issues, there's a lot of difficulty in modeling PDRs because the model grid is quite expensive to compute, mainly because each grid point encodes complex chemical dynamics. There's supposed to be another figure there. Let's see if it comes. Okay. So if you take one specific point that corresponds to and evolve the system, you get this sort of plot for that specific point. And for those set of initial conditions and those set of temperatures, you need to come up with a way of evolving all of these simultaneously. And the problem is that in a PDR, there's thermal processes contributing to the abundances of chemicals, and then these chemicals, the abundances of these chemicals then in turn determine the rates of those thermal processes. So it's sort of a coupled system where you're solving for both thermodynamics and chemistry. And this can be quite time consuming, especially if you have a large grid and it is possible that these parameters, for example, can span many different orders of magnitude. And so when you have these parameters spanning different orders of magnitude in different regions, it's quite complicated to model them. And that's what I mean by high dynamic range physical parameters. The other problem is that when you try to use PDRs in modeling, in larger simulations, for example, in cosmological simulations, you need to get information about both small scale effects, such as in PDRs, as well as in large scale effects, for example, when galaxy clusters merge. So when you want to model these small scale effects in cosmological simulations, it is quite time consuming, because this can be a huge bottleneck, because a lot of processes will depend on this, and this can significantly like make it expensive to compute. So this is where the idea of an emulator comes in. An emulator in general, they are used in different fields of science, not just astronomy, but the idea of an emulator is that it maps the same inputs to the same outputs. Like if you have a computational model that takes inputs and gives outputs, an emulator takes those same inputs, gives the same outputs, but it is statistical, and so it is much more faster to compute. Typically it is like a deep learning framework trained on chemical modeling data. People have used different kinds of emulators, different kinds of deep learning frameworks to construct emulators, but they can be quite accurate and very fast. Like you saw how a neural network can approximate anything you want, and neural networks are quite good at this. And one of the previous works that I like started with, or like I referred to, was like this work where they tried to produce an emulator that would predict the abundances of chemical species, and for that they used a framework called autoencoders. The problem with autoencoders is that if you try to use different sets of initial conditions, at least in that paper from what I understood, they had a hard time extending this to a larger parameter space. So this work was, my master's thesis work was essential because they wanted, like I wanted fast chemical modeling, and I also wanted a good coverage of the parameter space. This is what I was talking about when I said a high dynamic range parameter space. For example, like hydrogen column density can go from like 10 to the 5 to 10 to the 23. Something else can go from like 10 to 10 to the power 6. So like it's a completely different set of ranges, and all of these ranges are quite big. And you want to, and if you are sampling from like a parameter space like this, you want good coverage, and once you have good coverage of initial conditions, you want to accurately evolve a system for those initial conditions. And also I want to model more species. This is a typical example of what a chemical reaction network could look like. This one is specifically about formation and destruction of carbon monoxide. I don't know where exactly this is. It's probably in some, I would guess it is some form of emission nebula, or some place where there is a lot of star formation happening as well. So like there's all sorts of these dependencies which must be captured, and so you have a lot of coupled equations which you need to solve. So for this, yes, this is where I wanted to use NeuralODEs for. So for this I started with a parameter space, and like once I had a parameter space, I sampled from that parameter space. For that I used this specific method called Sobol sampling. It is like random sampling, but it sort of fits the, like it fills the parameter space a bit more uniformly. Like when I used random sampling, it was more, it did fill the parameter space well, but there were also a lot of gaps in between. When I used this method, it was a bit more uniformly filling the space, I would say. And so once I have, like each point here corresponds to one set of initial conditions, and I want to like evolve those initial conditions. The next step was to like take that and then generate models. Like by models I mean, here I mean like numeric, general computational models of PDRs. And these models will then serve as my data set for training an emulator on this. And the idea is that once you train an emulator on this, you want to be able to just provide initial conditions and let the emulator predict the dynamics of the system. And yeah, you want to take advantage of the emulator's ability to get these predictions quite fast. And that was the whole idea. And for in this one, I chose these three variables, or like, yeah, the initial conditions I chose were based on the Orion bar. That's why I showed that picture in the beginning. The idea was to capture the variations in abundances in these three areas, like the ionization of, like the transition of H plus to H, and then C to CO, and then also the molecular transition of like O to O2 and those kind of areas. And for this I also chose these sets of parameters. It was mainly these three parameters. These were the parameter spaces that I chose to then sample data from. I also wanted to see what the temperature evolution would look like, so I also set initial values for those, and I also included those as initial conditions to try and see how the system evolves. And I also set the initial abundances based on abundances in the sun. Apparently, for modeling nebulae, or like in general for modeling regions in the interstellar medium, solar abundances work quite well. Then the next step was to generate data. For that I used this software called 3D PDR. It can generate three-dimensional simulations of PDRs. You give it initial conditions. It basically does a lot of ODE solving, coupled ODE solving in the background, and it is quite parallelized and it's like quite optimized quite well. But because it solves coupled ODEs, it does take a lot of time to generate data. This was also like one of those benchmarked models. And yeah, it solves a lot of ODEs for chemistry and thermodynamics simultaneously, and so it uses a sort of ray tracing scheme to find how radiation gets attenuated, and based on that it evolves both the chemistry and the thermodynamics. In my situation, I actually used a one-dimensional simulation, so I didn't do three-dimensional simulations, but I'm just showing this because this was, I think, the first computational model that could do three-dimensional PDR simulations. So I used one-dimensional simulations and I generated data, and this is kind of what I'm just showing two molecules here, or like two species here, and I'm trying to show how their abundances vary as a function of like the depth into the PDR. This is I generated this for like a bunch of different values of those three parameters I talked about, and then I computed histograms of how they vary. But yeah, these were like 1024 sample points. I did this data generation for 5 species, or wait, I did data generation for I think 20 something species, but in the end I trained the emulator on just 5 species. But yeah, this data spans like many orders of magnitude. And one thing I want to highlight here is this trend where like atomic hydrogen's abundance increases as you go into the cloud, mainly because radiation gets attenuated. And like for H plus on the other hand, because as you go into the cloud it keeps getting absorbed, and so the abundances of H plus reduces as you move into the cloud. This was just to show you what the data distribution looks like, and you want the neural ODE to sort of capture these trends in the data. Oh yeah, this is what I was talking about, that like for ions because their abundances decrease, and for atoms and for molecules the abundances increase as you move into the PDR. You want to capture these sort of dependencies. And yeah, then like once I had this data set, I moved to the training part. I think here, okay, so I should mention that these slides are from my MSc colloquium. So some of them were used to, I think at that point I had to explain to a bunch of astronomers what neural ODEs were within one slide. So I had these pictures. I think this was from a specific example I took from that thesis I was talking about. This just shows how you get that outputs, and how you can sort of relate those outputs to the inputs based on, because these are like analytical. Your neural ODE is in the end, it has layers which in the end do sort of computations which you can relate analytically, and like that's how you try to find the gradients. So this was just to show that. And I think yeah, so I used like 5 abundances of 5 species, 2 temperatures, 3 of those parameters that I talked about. And this was a video that I made about how the training process looks like for those 5 species. You can see that there is a lot of oscillation happening. So that should tell you that like the loss landscape is quite complicated, and there are so many different points of local minima that you have to avoid. So you need to do all sort of like different tuning operations, I would say. Like you need to modify the learning rate here and there. You need to test different configurations, and you need to see what works well. So this was just a video to show you what the training process was like. In the end, I computed, like I had different, because I had like 1024 sample points. Each of them had a prediction, and so I computed a loss for each of those predictions. And then I took a sort of distribution, like I tried to model that distribution of losses, and I computed a histogram of those losses. And then there's like the 0th percentile loss, which is like the best fitting example, and then the worst fitting example is there. What I did notice was that the best fitting example corresponded to like typical conditions in the Orion bar, whereas the worst fitting examples had some of the parameters that are chosen there are a bit unphysical and you don't really see them. So this was a way of explaining why the NeuralODE could not really fit it well, because the data set it was trained on also did have like realistic initial conditions. So here it captures the variations in the abundances, and another thing is that similar to the example I showed you previously, I took like chunks of the data and then trained them for a few hundred epochs, and then I kept continuing that way. So the reason why I do that is so that you can so that errors don't accumulate as you try training it further. But in case of the examples where the errors are quite high, those errors do keep accumulating, and there's not much that can be done about it. And yes, you also need to, so because there are 3 parameters here, and all of these parameters contribute to these initial conditions, the idea was also to check how these losses vary when you vary those initial conditions. In general, I found that the sensitivity to these parameters were quite similar. I'll also show a plot about this a little later. So this is kind of what the training process looked like. I don't know if I showed a loss curve before, but the idea is this shows how the loss varies as a function of training. And in those regions where I introduce new data, like when I was talking about how I introduced a new chunk of data every 200 epochs, you see that there is a loss spike there. And then when the model learns the dynamics, it slowly reduces again and again. And the plot on the right was to show how this loss varies as a function of this depth into the PDR. So I have a lot of different data points, and all of them have something varying as a function of depth. Suppose I stack all of the, I do some sort of averaging across all of the other dimensions so that I only have the loss as a function of the depth into the PDR. You get something like this. My interpretation of it was that the places where the losses are high, those correspond to regions close to the transition zones where H plus gets converted to H and C plus gets converted to C and so on. Those are also the regions where the dynamics change quite severely, and so when there are minor variations such that it doesn't fit the model, if it doesn't fit the data point quite well, those errors sort of get accumulated here.
The loss is minimum at 200 epochs.
Yes.
So is it better to stop?
So in actually the loss that is being computed here is only up to that point. So it is not for the entire epoch, for the entire time series. That's why it looks like that actually. Yes, so yeah, this is what I was talking about, the loss spikes. There is this expected behavior of loss versus visual extinction based on what I think the transition zones look like. Yeah, this is the biggest gain from this process. To generate the whole data set, it took me 2 days of continuously running the PDR solver model. Once I train the emulator and I give a bunch of initial conditions, it gets predictions in 1 second, around that time. So this is I think it was 100,000 or a million times speed up in modeling. So this is the whole idea, or one of the biggest selling points of using emulators. Okay, this was another plot I made which shows how you have those losses for each of those samples, and imagine you sort of take this parameter space where those samples were generated, and you do a sort of three-dimensional histogram, and you try to add up the losses in a specific bin in that three-dimensional histogram. This was actually I took a while to understand how to make a 3D histogram, but yeah, here we are. In most of the places, you see that the loss is fairly small for like different combinations of parameters. There are some pockets where you see like there is a loss spike, especially like those yellow and green boxes. There is again no clear trend on why that happens. There is like my assumption of it was either that it was those spots corresponded to regions where the transition zones were pretty steep falling, or like because it was steep falling, the ODs, like the neural ODE was not able to capture that. It could also be because of like unphysical parameters as well. But usually in the general parameter range there, I did see that there was a good fit. And then I made another plot where it shows how these laws vary for different chemical species. The general idea is that in these kind of plots, you want to see that the predicted and true values are quite similar. You will see that like in most cases there is like a lot of the points do fall close by, but again there are some points where, like in some examples where they don't really fall close to the true values. This is again, I would say I would attribute it to like unphysical initial conditions, but I did notice that the T gas predictions were quite good. Like you see a concentration of a lot of different points here. It was also, I think, because gas temperature variation wasn't that high, and it was, I think, easy for the model to get those predictions. And this is actually one caveat I mentioned. Like the data set had like 29 different species, but I trained it only on 5 species. The idea of this project was to make a prototype of trying to see whether NeuralODEs are a good candidate for producing emulators. And so I started with training on 5 species, and so all the results you see here are for a data set of 29 species, but for a NeuralODE trained on 5 species. So the natural extension was to like get a larger data set, train it on a larger number of species, because like the initial data set of chemical species I was talking about, there's something like 300 different chemical species there. And so if you can produce an emulator that sort of models all of those 300 species for different like physical conditions in the interstellar medium, I think that's really like, it's where you want to be, I would say. So based on my work, there were also a bunch of other papers that came out. They extended this work to more like to more chemical species. They also modified the architecture quite a bit, and so yeah, there's like 2 different papers. I can, if you are interested, I can send them to you as well. So then I will quickly talk about the applications of emulators. The biggest application is that because they're quite fast, you can use them to speed up sort of large-scale hydrodynamical simulations. Because these large-scale hydrodynamical simulations incorporate so many different effects, like stellar feedback, or like understanding galaxy morphology, or like trying to predict cosmological parameters. For all of these things, you need to model so many different effects at so many different length scales. And a PDR is actually a very, very small length scale in the grand scheme of things. So if you actually don't get this modeling right, these errors then propagate to large scale effects, and then you have a big problem. So the idea of these emulators, especially PDR emulators, is to then get like fast and accurate computations of like PDR models, so that in the end they can then be efficiently used in hydrodynamical simulations. Let's see, yeah, because the computational speed up was about 10 to the power 5 times, they can really be a really viable candidate for speeding up hydrodynamical simulations. As I was talking about, there are so many different physical effects you need to model at so many different scales. So you need to get that right, and you also in the end can use this to understand how chemical species evolve with time as well, and like how they can be used to understand the evolution of the universe as well. Another application was, actually this was one of the motivations of my project. It was that when JWST came out, and one of the first observing cycles they did was on the Orion Nebula and like nearby regions, they actually found that with very high resolution observations, they actually found the presence of a protoplanetary disk in the PDR, in the region where the PDR is. And this was interesting because general PDR models don't really take this into account. So you want to sort of, because these NeuralODE based emulators can model the dynamics to arbitrary precision, you can then do really high resolution modeling, and with the hope that when you capture these high resolution dynamics, those dynamics can then help you understand features that you haven't seen before, or like physical phenomena that you haven't seen before. Yeah, so you like for model something like this, you need to use like stiff equations. It's definitely like a situation where you have like multiple physical processes contributing to very different time scales, so you need to take this into account. But when an emulator is trained on a data set with like varying time scales, they can become like quite good at modeling, and you can use them to get different sorts of outputs from them. And so this is the idea of like taking high resolution emulators and then trying to model what are called emergent phenomena from them. The idea of emergent phenomena is that when you have a system where you have a set of constituents, and those constituents by themselves don't tell you a lot of information, but then when you put that system together and you try to model that, because of the interactions between those constituents, you get phenomena that you couldn't explain otherwise. Because NeuralODEs can be modeled to arbitrary precision, the idea is to use these kind of emulators which use like differentiable solvers to then model emergent phenomena. This is actually work in progress. It's like people are actively working on developing emulators and like fitting them into simulations and then trying to get their outputs, and then in the long run this would be useful in planning observations. So now there is a lot of work going on in like building foundation models, general purpose models, AI models which can model a wide range of effects. You need a like really large amounts of data for that. One example of a foundation model is like language models like GPT and Gemini are foundation models trained on the entire internet. They've basically like processed all of the text on the internet to like train these models. Similarly, you can like, there are people who develop foundation models in astronomy now, and the idea of like when you develop foundation models in astronomy, you want them to follow different sorts of scaling laws, physical laws. You want them to produce realistic predictions, and so there's like significant work going on in this right now. I think the final thing I want to show is an application that's called like likelihood free inference. Normally, if you have a data set and you want to take the example of, let's say, predicting cosmological parameters from all the data sets you have like prior knowledge of all the information that you've collected, and based on that prior model you build something called a likelihood, which relates the data that you have to your understanding of the models that you have now. And then based on this prior and the likelihood, you want to compute a sort of posterior, which gives you an idea of a distribution of what your final parameters that you want to estimate look like. But the problem, so this is traditional like Bayesian inference. When you do inverse modeling, you use like some MCMC sort of method to get estimates of those posterior parameters. But often this likelihood is nearly impossible to compute because there's so many different dependencies that you need to take into account. There's like you might have to do a lot of high dimensional integrals, like because of these kind of computational difficulties. Often you either don't know what a likelihood looks like, or it's just extremely difficult to model it. And so the idea is that if you have an emulator that is trained on data, you basically use that data. Yeah, so like you use this knowledge of numerical simulations and you train an emulator on the simulations. Because the emulator is fed initial conditions, you have some knowledge of parameters which describe your model, and the simulations that you get are your data. So you sort of have a likelihood when you have simulations and you train an emulator on it. And because that emulator learns representations in that data, you can then use it to make different sorts of computations, or you can just attach another neural network to those representations, and then you can try to get estimates of parameters that you do want to estimate, which would be quite difficult to do via traditional Bayesian inference. And so this was one of the final applications I wanted to talk about. I don't have a summary slide for the second half, unfortunately, so I'll leave it at this slide and take questions. Thank you. Any questions? Okay, I guess feel free to reach out if you have questions. Sure, yeah, I can.
And also, so I'm personally not from an astronomy background, but I was interested in learning about the NeuralODes and their applications.
Okay.
Could you recommend some resources?
Yeah, I can share some resources. There's like a few different papers, and there's like a very good PhD thesis on NeuralODes. Sorry? Yes.
I am aware of it, but I found it a bit complicated.
Okay, I think there are a few blogs I found as well which were quite good. I can share that to you. Yeah.